Welcome to the Physics GRE GR0877 solutions presented by yours truly, the Rogue Professor. So the first thing I want to point out about solutions in this exam is that we always want to be mindful that we're going to be given a table of information that has a lot of constants that you need not memorize, and there's also a prefix for powers of 10 that's given to you. So we don't want to concern ourselves about memorizing how to convert a picometer to a millimeter, etc. We can always refer back to this table of information when we're taking the actual exam. Another thing, interestingly, that the Physics GRE gives us is the rotational inertia about center of mass, and there's a couple of equations down here for the rod, disk, and sphere. So we're going to refer back to those as well. So let's jump into the solution. The first problem, a ball is thrown out of the passenger window of a car moving to the right, ignoring air resistance. If the ball is thrown out perpendicular to the velocity of the car, which of the following best depicts the path the ball takes as viewed from above? So as the problem states, there's no air resistance, so the only force acting on the ball when it's released is gravity, which pulls the ball down, and it can be ignored since we're viewing the ball from above as the problem states. So the ball is an inertial object. It's going to continue to move to the right with the same velocity in the x direction as the car. The velocity in the z direction is the velocity at which the ball was thrown out of the car. There's no acceleration in either of those coordinates, so there's going to be no curve in the path. And the ball is going to continue moving forward as viewed from above by a stationary reference frame. So the answer that depicts that is answer B. Number 2, here we go. An object is thrown horizontally from the open window of a building. If the initial speed of the object is 20 meters per second and it hits the ground 2 seconds later, from what height is it thrown? Again, we're going to be able to neglect air resistance, and we're going to assume the ground is level according to the problem. So you've got to know your kinematics. So this is one of the examples, and it's going to be one of the kinematic equations where the height equals 1/2 acceleration times time squared plus the initial velocity times the time. So in this problem, the acceleration is going to equal g, which is gravity pulling it down at 9.8 meters per second squared. Our initial velocity is going to equal 0. And so therefore, just plug in those numbers. Our height is going to equal 1/2 times 9.8 meters per second squared times 2 seconds, that quantity squared. It's going to equal 19.6 meters, and that is D. Number 3, we're making some progress. A resistor in a circuit dissipates energy at a rate of 1 watt. If the voltage across the resistor is doubled, what will be the new rate of energy dissipation? So here we're going to apply Ohm's law, where the power equals the voltage squared over the resistance, and if the voltage of the final voltage is 2 times the initial voltage, then the power is going to equal 2 times voltage squared divided by the resistance, and that equals 4 times, you apply your square to the 2, 4 times voltage squared divided by resistance. Our power equals our initial power equals 1 watt, and that, remember, equaled the voltage squared over the resistance. So P2 is going to equal 4V squared over R, and that quantity is 4P1, P1 being the initial power, and that's 4 watts. And that is going to be letter, can you guess? E. Okay. Number 4. Getting into some fun ones now, and I want to just point out that in the bottom right we can keep track of how many of us got the problem right, how many got it wrong, and we can keep track of really how hard the problem is. So always want to keep track of that number in the bottom right, and it can really let us know, was this a hard problem, was this an easy problem? And that can give us kind of a comfort feeling when we're working through these, given that we know the answers and we have the solutions here. So number 4, an infinitely long straight wire carrying current I1 passes through the center of a circular loop of wire carrying current I2, as shown above. The long wire is perpendicular to the plane of the loop. Which of the following describes the magnetic force on the loop? So it's an infinitely long wire. It's at a 180-degree angle to the loop of the wire. It's above and it's below the loop. So the magnetic force from the current I1 on the loop of the wire is going to be QVB, where B is the magnetic field, times sine theta, where theta is the angle, and the angle is going to be these two angles here because we have above and below the loop. So the magnetic field is going to equal B is going to equal the magnetic constant times the current of the I1, the current in the first length of wire, divided by 2 pi r. So theta here is going to equal 180 degrees, which is the amount above and the amount below. 90 plus 90 is 180 degrees, and the sine of 180 degrees is 0. So our force from the current I1 on the loop of wire is going to be QVB sine 180 degrees. Sine 180 degrees is 0, therefore the force is 0. Number 5. De Broglie hypothesized that the linear momentum and wavelength of a free massive particle are related by which of the following constants? Gotta know this is such a basic one. Energy equals momentum times the speed of light equals Planck's constant times the frequency, F, and therefore lambda times the frequency equals the speed of light, which is a constant, and therefore we can derive that the momentum times the speed of light equals Planck's constant times the speed of light divided by the wavelength, and therefore the wavelength simply equals Planck's constant divided by the momentum. So that is going to be A, Planck's constant. Number 6. An atom has filled n equals 1 and n equals 2 levels. How many electrons does the atom have? So this is a basic equation we're going to have to just carry with us through the exam. The nth shell of an atom can hold 2n squared electrons. So we're going to need to add these shells up because there's 2 of them. The first shell holds 2 times 1 squared, which just equals 2. The second shell is going to hold 2 times 2 squared equals 8 electrons. So how many do both combined hold? 2 plus 8 equals 10 electrons. That is going to be letter E. Number 7, the root mean square speed of molecules of mass m in an ideal gas at temperature T is, now we're going to apply here that the kinetic energy, 1/2 mv squared, equals the thermal energy, 3/2 kT. And we have 3 dimensions of space here, so that's where that 3 comes from on the right-hand side. So we're going to get v squared equals 3 kT over m, the mass, and then just take the square root of both sides. Velocity equals 3 kT over m, that quantity, square root. So that is going to be answer C. Number 8, the energy from electromagnetic waves in equilibrium in a cavity is used to melt ice. If the Kelvin temperature of the cavity is increased by a factor of 2, the mass of the ice that can be melted in a fixed amount of time is increased by a factor of... So let's get started just with the power equation, which is going to be the power that is required to melt the actual ice mass, and the power equals work divided by time. So the Stefan-Boltzmann law is the power equals A/E sigma t to the 4th. The important thing is the t to the 4th. The power is dependent on temperature raised to the 4th power. So twice the temperature in the same amount of time is going to equal basically 2t. It's going to be proportional to 2t to the 4th. Remembering that T1 is the temperature, initial temperature, and so if we take 2 times that, 2 raised to the 4th power is going to be equal to 16 times the initial power. Figure above, number 9, represents the orbit of a planet around a star S, and the marks divide the orbit into 14 equal time intervals. T equals capital T divided by 14, where the capital T is the orbital period. If the only force acting on the planet is Newtonian gravitation, then true statements about the situation include which of the following? Kepler's laws. Easy to remember, a good thing just to memorize for the exam. There's a good chance you're going to get one Kepler's law thrown at you. So let's just walk through them. The first law, all planets move in elliptical orbits with the sun at one focus. Okay. Law number 2, a line that connects the sun and a planet sweeps out equal areas in equal times. Okay. Law number 3, the square of the period, capital T, is proportional to the cube of the semi-major axis of the ellipse. So, number 1 and number 9 is going to be the second law. Okay, so that's true. Number 2 is going to be the first law. And number 3 is exactly the third law, which is the square of the period is proportional to the cube of the semi-major axis of the ellipse. What's the semi-major axis? The semi-major axis is the wide horizontal radius. So you can think of it as the elongated version of what you would call the radius in a classical circle. So you can see how it's elongated. So those are simply Kepler's 3 laws, and it's going to be answer E, which is all 3 of those are correct, and those are Kepler's laws. And we're going to do 10 problems at a time. We don't want to try to overdo it in each segment. Pick up each video, do 10 problems, figure out how they're done, walk through the solutions, and get your energy back and pick up another set of 10 problems as we go through these exams. There's going to be 600 solutions in total, so it's definitely going to be a marathon, not a sprint. So number 10, a massless spring with the force constant K launches a ball of mass M. In order for the ball to reach a speed V, by what displacement S should the spring be compressed? So we're going to apply the energy conservation principle here. Say that the energy of the spring, 1/2 kx squared, equals the kinetic energy of the ball, 1/2 mv squared. So from there you can get where x is equal to s in this problem, which is the displacement. X squared equals mv squared over k, the spring constant, and x simply equals the velocity times the mass divided by the spring constant k, that quantity, m divided by k, square root. So I hope these helped, and we're going to continue with more solutions to this test. So go ahead and find them, keep powering through them, and if you stick with me through all 600, I'll be very impressed. This is going to be a fun adventure going through these solutions together.